Before you begin working through these practice exercises, you need to get what I call a toolbox full of things that you will need to successfully do these problems. And this is probably a decent listing of most of them anyway. From Chapter 3, you need your 5 basic truth tables, and I developed those from the what I call memory aids for negation and or implication and by conditional. You need to know your two De Morgan's laws, and you need to know the disjunctive and conjunctive forms listed for an implication and the negation of an implication. And from Chapter 12, we talked about tree diagrams and using tables and lists. We talked about the counting principle, permutations, just plain factorials, combinations, counting when some of the objects are indistinguishable from each other. Then we talked about our basic definition of probability, and we talked about odds. So you have to know those things well before you can really even begin to tackle these problems. Let's look at some problems from the Test 2 practice set. Number 1 says determine the truth value of the compound statement given, and we know that P is a true statement, Q is a true statement, and R is a true statement. So the compound statement is given, but we know that P is true, so you can actually put capital T in place of P to indicate that it's true. We know that Q is true, so again you can replace Q with a capital T, and we know that R is true, so we can replace R also with a capital T. At this point, we just work inside the parentheses and take one step at a time. First thing I notice is that there's a not T, and I know that the negation of T is F, in other words, is false, so I can put that in. And then you want to work inside the parentheses, so you've got false or true. Now we know that the memory aid for or is it's only false if they're both false. Those are not both false, so that would be true. That leaves me with the expression true or true. And again, an or is only false if they're both false, so true or true is true. Number 2, determine the truth value of the compound statement given that P is a false statement, Q is a true statement, and R is a false statement. So I look at the compound statement, and everywhere I see a P, I put in capital F to indicate that P is false. Everywhere I see a Q, I put in a capital T to indicate that Q is true. And everywhere I see an R, I put in a F, capital F, to indicate that R is false. Having done that, I work inside parentheses and work my way out. First thing I notice, I've got two negations. The negation of true is false, and the negation of false is true, so I can get rid of both of those, change the not T to an F and the not F to a T. And then moving left to right, I have false and false inside parentheses, so I want to work inside the grouping symbols. And is only true if they're both true. Well, they're not both true, so that means that and is false. I can also look at inside the parentheses at the end of the statement and see a false or true. And remember, or is only false if they're both false. But false or true, of course, is true. It takes both being false to get a false, so false or true is true. Now moving back to the last grouping symbols, on the left, I see a not false, so that means it's true. And then I have a true or false inside of grouping symbols, so I want to work with that. And an or is only false if they're both false. They're not both false, so that means that grouping is true. And I'm left with true and true. And the memory aid for an and is only true if they're both true. They are both true, so I get true. Number 3. Determine the truth value of the compound statement given that P is a false statement, Q is a true statement, and R is a true statement. Remember my memory aids for and or. And is only true if they're both true, or is only false if they're both false. I know that P is false, so everywhere you see a P, put in a false. I know that Q is true, so everywhere you see a Q, put in a capital T for true. And R is also true, so everywhere you see an R in that original statement, put in a capital T for true. That gives me a complex logical statement, but I'm going to work at it in organized fashion. The first thing I'll do is get rid of these negations. I know that not false is true, and I know that not true will be false, so I'll make those replacements. And then I begin working inside the grouping symbols. That first grouping symbol has true, and remember, an and is only true if they're both true. Those are both true, so that will turn out to be true. Then I see my next set of grouping symbols, that false or false, and an or is only false if they're both false. Well, they are both false, so that grouping symbol will yield false. Now my only remaining grouping symbol, I have false and true, and again, an and is only true if they're both true. They're not both true, so that means it's false, and that leaves me with true or false, and an or is only false if they're both false. They're not both false, so that means it's true. Number 4, construct a truth table for the compound statement. So they've built the basic truth table for you, and they've put in the values for P and Q, and you have to complete the rest. So the first thing I would do is just copy the Q column over from column 2 into column 3. So you get true, false, just copy that directly over into column 3. Also remember, you're going to be using your memory aids for and or at some appropriate times. I'll go ahead and pop those up there. You also notice that there's a not P column, 1, 2, 3, 4, 5, the fifth column. Well, you know that P is true, true, false, false. That means not P would be false, false, true, true. Now that you know the values of the third and fifth columns, you can calculate the and value in the middle. And again, the memory aid for and is it's only true if they're both true. So if you go down and look at that set of columns, you can see that the only place where you have true and true is the third row. So when you do the and, you get false, false, true, false. And again, the only true is when both the left and the right side of the and were true. And then you would move over to the last column in the table, which is not Q. You know that Q is true, false, so that means not Q would be false, true, true. And now you need to do an or on that, and an or is only false if they're both false. So if you look, you only have both false in the first row. And so you get false, true, true, true. Number 5, use two truth tables to show that the pair of compound statements are equivalent. So they give you the statement P ORed with the grouped Q and not P. That's the left truth table. And then the right truth table is the P or Q. So you're going to complete both truth tables and show that the values are the same. If they're not the same, the statements are not equivalent. So put in the P column. The P column was true, true, false, false. So the true, true, false, false just gets copied over to column 3. You might also then move over to the column with the Q. And again, the Q column is true, false, so when you copy it over, it'll be true, false, true, false. The very last column is the negation of P. So if you look at the P column, it's true, true, false, false. The negation of P column will be false, false, true, true. Now you can work with those last two columns that you filled in to fill in the and value. And the and is only true if they're both true. Well, there's only one place where they're both true, and that's the third row. Everything else will be false. And finally, now that you have that, you can calculate the or value. And remember, on the left, you're using the T, T, F, F, the third column values. And on the right, you're using the F, F, T, F, and that's the 1, 2, 3, 4, 5, the sixth column. And when you're doing an or, it's only false if they're both false. But if you look through there, only the last row is both falses, so everything but the last row will be true. So we've done the truth table for the complicated logical statement. Now let's go over and do the truth table for the simple statement, P or Q. Remember, an or is only false if they're both false. Well, there's only one place they're both false. That's the last row. Everything else is true. And now if you compare the truth values that you got from the first table with the truth values you got from the second table, you'll see that those two statements are indeed equivalent. Number 6, make use of one of De Morgan's laws to write the given statement in an equivalent form. And the statement is, it is not true that she received a promotion or that she received a raise. Now you've got to remember, De Morgan's laws tell you how to take the negation of an and statement and how to take the negation of an or statement. This particular statement has an or, so you're looking at the negation. When the phrase that says it is not true that means it's a negation, and the or means that we're using the version of De Morgan's laws that works with an or. And the statement she received a promotion would be like the P statement in De Morgan's laws, and the statement she received a raise would be like the Q statement in De Morgan's laws. So what does De Morgan's laws say about the negation of an or? Well, the negation of an or is an and the negation symbol is treated pretty much like a minus sign if you were just doing algebra with a minus sign. So that negation symbol distributes, and the symbol or flips and becomes an and. And that's what De Morgan's law said. To take the negation of an or, it becomes an and with both P and Q negated. So we're looking for the one that says the P is negated. P was she received a promotion, so the negation would be she did not receive a promotion. You're also looking for a statement that has an and in it, and then the Q has to be the negation of she received a raise, so that would be she did not receive a raise. By elimination, you can see it has to be statement number 3. She did not receive a promotion is the negation of P. She did not receive a raise is the negation of Q, and it uses an and instead of an or. Number 7, explain why the statement 8 is less than or equal to 9 is a disjunction. This problem really, as soon as you read it out loud, you've already answered it. That expression is 8 is less than or equal to 9. Number 8, determine the truth value of the given statement. If all frogs can dance, then today is Monday. Well, think about this. An implication is only false in one case, and that's the case where you have true implies false. So you've got to look up at that statement and analyze it. P is like the statement, frogs can dance. Q would be like the statement, today is Monday. So I think everyone would agree that all frogs can dance is false. But if you look down, an implication is only false if it starts off true. Well, that one already starts off false, so it doesn't really matter whether today is Monday or not, because false implies false is true, and false implies true is true. So when P is false in an implication, the result is going to be false regardless of what Q is. So the fact that they said today is Monday, if that statement were said on Monday, it would be true. If that statement were said on a non-Monday, it would be false. But in reality, it doesn't matter because the all frogs can dance part is false, and that assures you that no matter which case it is for the today being Monday, the implication itself will be true. Number 9, determine the truth value of the given statement. If the absolute value of x is equal to 7, then x is equal to 7. These type of problems where the open statements have variables, it's probably easier just to analyze the statement from a common sense perspective rather than trying to make it shoehorn into the rules. I think I can just think about this and figure it out, because I know that if the absolute value of x is equal to 7, then x could either be 7 or it could be minus 7, because the absolute value of 7 is 7, but the absolute value of minus 7 is also 7. So what I'm really saying is, if x is plus or minus 7, then x is 7. Well, that's obviously false. If x is 7, then x is 7. But if x is plus or minus 7, then you don't necessarily know that x is going to be 7. So I think that's probably the best way to do it. When you see a problem like this, just think about what it really is saying. And if you do, you figure out pretty quickly that that's a false statement. Number 10, construct a truth table for the following statement. And they built the truth table for you and put in the p-value and the q-value for the p column and the q column. So you need to finish it out. First thing I would do is remember that my memory statements, we're using an and we're using an implication. So I would put those up. And is only true if they're both true, and the if then or the implication is only false in the one case where p is true and q is false. P is true, true, false, false. So I put true, true, false, false in the p column. And then I'd move over, maybe I say, well, there's another p column. I'll go ahead and put that in there as well. There's no definite order you have to do these in. There are some things you can't do till other things are done. But beyond that, you have some flexibility in what order you do them in. So I decided I'll just go ahead and put in the p column in both places. There's also a q column. It's actually the last column, so I'll go ahead and put that in. Q is true, false, true, false. So that last column becomes true, false, true, false. And there's also a not Q column, so I'll take the Q column, which is true, false, and make it false, true, false, true. Once you get to this point, you're probably just going to want to move back to the left and work from left to right. Looking at that, you've got to evaluate an and is only true if they're both true. If you scan through that, only the second row is both true. So the second row will have a true, but the other three will be false. And then you want to move over to the and on the far right. And again, an and is only true if they're both true. If you look, only the first row is true on both sides. The rest then will be false. And now that you've got those, do the not. That means all the and values change to their negation. So not true is false, not false is true, not false is true, not false is true. Now you're ready to look at the implication, and you're using the values under the and on the left of the implication, and you're using the values under the negation for the right side of the implication. You always use the values under the very last column you did on each side. So now we've got to remember that an implication is only false if you get T implies F. So if you look through there are no T implies F's at all. So the whole thing is true. So that turns out to be a tautology. Remember, a tautology is a statement that's always true. Number 11, construct a truth table for the given statement. Now they've built the truth table for you, leaving lots of blanks, of course. They've given you a P column filled out, a Q column filled out, and an R column filled out. I think I would just start with the P column and propagate it. The first open column is P, which is T, 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 F, 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 F. Let's copy it over. If you notice that a little over halfway through the table, there's a not P column. That means to change all the values to their negation, so those first four truths become falses, and those last four falses become truths. Then move to the Q column. Notice that about a third of the way in, or a fourth of the way in, you've got a Q column. Q is true, true, false, false, true, true, false, false, so just copy that over. And then notice that the very last column in the table is a not Q. That means we're going to change everything to the negation. So true, true, false, false, true, true, false, false becomes false, false, true, true, false, false, true, true. And then do the same thing with the R's. Notice about halfway through the columns you have an R. R goes true, false, true, false, true, false, true, false. You copy that over. The third from the end is also a column that has an R. So it also becomes true, false, true, false, true, false, true, false. And at this point, I would just go back to the left and try to work my way through the best I can, starting with that implication. Remember, for an implication, there's only one case where it's false, and that's T implies F. If you look through there, T implies F appears in the third row and the fourth row. So those two are false, but they don't appear anywhere else, that combination, so the rest of them are truths. Now you can't do that OR column until you get what's on the other side of the OR, so we have to move over and do this AND. Now remember, the shortcut memory aid for AND is only true if they're both true. if you look, 1, 2, 3, 4, the 5th row is both trues, and the 7th row is both trues. The rest of them are going to be falses. Now that we've done that, and we see that there's another OR that's grouped together, those last 3 columns, and that's an OR. And the shortcut for OR is it's only false if they're both false. If you look through, row 2 is both falses, and row 6 is both falses. So the others are true. At this point, I'll go back and do the OR. I have enough information to do the OR. Remember, the last column I did on the left was the one I've circled, and the last one I did on the right of the OR is the one I've circled. So we've got to OR those 2 columns together, and the shortcut memory aid for an OR is only false if they're both false. And if you look through there, the 3rd row has 2 falses, the 4th row has 2 falses, and that's it. So the rest of them are true. And last but not least, I've got to do the implication. So the left part of the implication, the last column that I did on the left was the OR, so that's the one that I use. And the last column that I did on the right side of the implication is under the OR, so those are the 2 columns I use. And I'm doing the implication. And remember, the only time an implication is false is in the true implies false case. So if I look through there, the 2nd row is true implies false, and the 6th row is true implies false. So those 2 are false, and the rest of them are true. And so now my final result are the truth values under the implication, and I've completed that truth table. Number 12. State whether the given biconditional is true or false. Assume that x and y are real numbers. And the statement is x squared is equal to 4 if and only if x is equal to 2. As I said in an earlier problem, for statements like this, these open statements with variables, it's probably easier just to analyze a statement from a common sense viewpoint rather than try to shoehorn them into the rules that we've used before. At least in my opinion it is. And what I notice is the first statement, x squared equal to 4, is the same thing as saying that x could either be 2 or minus 2, because 2 squared is 4, but negative 2 squared is also 4. So that means you're saying x equals plus or minus 2 if and only if x is equal to 2. Remember, a biconditional is only true if they match. Well, if x could be plus or minus 2 on the left and could only be 2 on the right, then there's a chance that they don't match. So that statement would be false. Remember, for a biconditional, it's only true if they match. 13. State whether the given biconditional is true or false. 5 is equal to 6 if and only if 3 is equal to 8. As I said earlier, if and only if or a biconditional is true only if they match. They're both true or they're both false. Well, obviously 5 equals 6 is a false statement. If and only if is the biconditional, the double-headed arrow. And 3 equal 8 is also false. So the biconditional is false if and only if false. And false matches false. So biconditional is true if they match. And they do match here, so the statement is true. Number 14. Write the sentence in symbolic form. Use V, P, and T as defined below. V is the sentence, I will take a vacation. P is the sentence, I get the promotion. And T is the sentence, I will be transferred. And the compound statement that we want to translate is, if I am transferred, then I will not take a vacation. So if you look back above, the I am transferred is the T statement. You don't have to worry about the tense so much. It says I will be transferred, I am transferred. That's just a matter of tenses. And I will not take a vacation is the negation of I will take a vacation. And the if then itself is the implication, which is the arrow pointing to the right. And then you just look and see which one it is, and obviously it's choice number 3. Number 15. List the elements of the sample space defined by the experiment and enter your answers as a comma-separated list. So we want to select an even single-digit whole number. Well, whole numbers start with 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you want to stop at single digits, you can't go any higher than 9. But they also want them to be even. So you have to throw out the odds. So the single digit even whole numbers are 0, 2, 4, 6, and 8. 16. List the elements of the sample space defined by each experiment. This experiment says we're going to toss a coin and then choose a digit from the digits 1 through 5. Well, think about it. We're going to toss a coin, and I think a tree diagram is perfect here. So it could either be heads or tails. Now you're going to pick digits, and you're only picking from 1 to 5. So if you read down that tree diagram, that gives you H1, H2, H3, H4, H5, and then T1, T2, T3, T4, T5, and you can see that that is choice number 1. And I think if you do it with a tree diagram, you'll find that that's the easiest way to do it. 17. Use the counting principle to determine the number of elements in the sample space. 2 digits are selected without replacement from the digits 1, 2, 3, 4, 5, 6, 7, 8. So remember, we've got 8 digits, and the counting principle says if we're choosing 2 digits, that's a 2-stage experiment. The number of ways to choose the first digit is the first stage, and the number of ways to choose the second digit is the second stage. The counting principle says we need to count each of those 2 stages and then multiply. So if you're selecting any digit 1 through 8, there are 8 numbers you could choose for the first digit. Now we're selecting without replacement. What that means is once you've chosen a number, you can't choose it again. So if we're doing it truly without replacement, whatever digit we chose originally, we can't choose that next time, so we only have 7 choices for the second try. And the counting principle says you multiply 8 times 7 to get 56. 18. Use the counting principle to determine the number of elements in the sample space, the possible ways to complete a true-false examination consisting of 20 questions. Now, if you think about this, it's hard to write out, but this is a 20-stage experiment. The first stage is the number of ways to answer question 1. The second stage is the number of ways to answer question 2. The third stage is the number of ways to answer question 3. And then finally, you get out to the number of ways to answer question 20. But the key thing here is it's a true-false test. So for a true-false test, you only have 2 choices, true or false. So there are 2 ways to answer every single question. And that ends up to be 2 times 2 times 2 times 2 until you get 20 of them. That's the same thing as saying 2 to the 20th. And on your calculator, you can use the power button and you'll find out it's 1,048,576 possible ways to answer a 20-question true-false exam. 19. 2-digit natural numbers are formed with replacement from the digits 0 through 9. How many numbers are greater than 45? This is a little bit tricky because starting at 45 makes you have to think a little bit more. The digits are 0 through 9. And you want them to be 2-digit natural numbers. And since you're choosing 2 digits, you know the counting principle will kick in and you'll find the number of ways to choose the first digit and the number of ways to choose the second digit and multiply them together. But the tricky part is starting at 45 is problematic. There are 6 digits possible if you're going to start somewhere in the 40s. You don't want to choose the first digit to be a 0 or a 1 or a 2 or a 3 because even with a 3, the biggest you could get is 39. You want something to be 45. If you start with 4s, you get 40 and 41 and 42 and 43 and 44 and 45 and 46 and 47 and 48 and 49. That's going to be too many because we actually want to start at 45. But let's put that aside for the moment and find how many 2-digit numbers that are 40 or larger. Well, if I want them to be 40 or larger, I can start with 4 or 5 or 6 or 7 or 8 or 9. That's 6 possibilities. The second digit can be anything. And there are 10 digits, so there are 10 possibilities. Now, the reason this is tricky is that 6 times 10 equals 60 is really telling us how many numbers are 40 or larger. But we want to know how many are 45 or larger. So you have to think about we've counted 40, 41, 42, 43, 44, and 45. That's 6 things that we counted that we didn't need to count. So we really got to take that 60 and subtract off the 6 things that are in the 40s that we didn't mean to count. And so you end up with 54. Now this is the way they meant for you to work this problem, but I will tell you, we learned something on the last test that would make this problem actually easier, and that is, if we're trying to count the numbers greater than 45, that'd be 46, 47, 48, all the way up to 99 if you want to stay in 2 digits. We learned a formula for counting consecutive integers, and if you remember what it was, it's the largest minus the smallest plus 1. That formula only works for consecutive integers, but that's what this is. So if you put 99 in for the largest and 46 the smallest, you end up with 54. Just what we got doing it the other way, but using the formula we learned in the last test material is actually the easiest way to do this problem. Number 20. 4 cards labeled A, B, C, and D are randomly placed in 4 boxes, A, B, C, and D. Each box receives exactly 1 card. In how many ways can the cards be placed in the boxes? So we've got 4 cards, A, B, C, D. You can't put the same card in 2 boxes. So if you've got a card labeled A, when you put it in a box, it's not available to be put in another box. So what that means is we're choosing without replacement. Got to be clear on that. Okay, we're choosing without replacement. The counting principle says this is a 4-stage experiment. We're going to put a card in box A, we're going to put a card in box B, we'll put a card in box C, and we'll put a card in box D. Now in the beginning, you can choose any card you want, so there are 4 of them. But you can't reuse that card. Once you drop that card in a box, it's gone. So you only have 3 choices for box B. That leaves you only 2 choices by the time you get to box C, and by the time you get to box D, there's only 1 card left. So by the counting principle, it's 4 times 3 times 2 times 1, which is 24. And the key to this problem was realizing that having only 1 card with each letter on it means that you can't reuse that card because it's impossible to put that same card in more than 1 box. So you're drawing without replacement. Number 21. A state lottery game consists of choosing 1 card from each of the 4 suits in a standard deck of playing cards. There are, of course, 13 cards in each suit. Count the number of elements in the event that an ace, a king, a queen, and a jack are chosen. First thing I'd say is that you have to make sure you are familiar with the standard deck of 52 cards. We're looking for an event that includes only aces, kings, queens, and jacks. So the first thing I would say about that is we just need to get rid of the rest of the cards. We are only interested in this event, aces, jacks, queens, and kings. So if you just collapse this and get rid of all the things in the middle that aren't aces, queens, kings, and jacks, you're left with those cards, the aces, jacks, queens, and kings. From that, we will be choosing 1 card from each of the 4 suits. So if you think of it this way, if you're going to choose from the clubs, you've got 4 choices. You can choose either an ace, king, queen, or jack. So there are 4 ways you can choose the first suit. Once you've chosen that suit, you don't want to reuse whichever card you chose. So there are only 3 choices for choosing. The way I've written it here is spades, but whichever suit is second. So there are 3 ways to choose the card from the second suit, and by the time you move to the 3rd suit, which in my example is heart, but it could be any of the suits, you've already used 2 of the cards, so there are only 2 left. And of course, by the time you get to the last suit, there's only 1 possibility that will give you 1 of each. So by the counting principle, 4 times 3 times 2 times 1 is equal to 24. So there are 24 elements in this event. Evaluate the expression 7 factorial minus 5 factorial. This is strictly a practice with your calculator. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. The best way, though, is to use your calculator. Remember that Shift 3 does factorials for you. So the easiest way is to press the 7 and then do Shift 3 and then hit minus and do 5 Shift 3 and then press equal. And that will give you 4,920, and that's certainly the easiest way to do it. Number 23, evaluate the expression permutation of 9 things taken 2 at a time times the permutation of 6 things taken 5 at a time. Again, this is just a calculator practice problem. You start off with the calculator, remembering that Shift 1 gives you permutations. You type in the big number, which is the 9, you press Shift 1, then you put in the smaller number, which is 2, you press equal, then you're multiplying, so you press the multiplication key, and then you start the second permutation. The big number goes in first, so you type 6, then you do Shift 1 for permutation, then you enter the smaller number, which is a 5, and you press equal, and when you do that, you will get 51,840. 24. Evaluate the expression, and it's a combination times a combination divided by a combination. Now, word of warning about a problem like this, that division symbol means that if you just carry out that calculation on a calculator and divide, you may not come out with an exact answer. You may get a decimal where the calculator just runs off the screen. It doesn't have decimal places. Now, in this course, if you're asked to evaluate something, unless they tell you to round it, you have to have an exact answer. So what I'm saying in all this is, with this particular type problem where you're doing a combination over a combination, it's better just to get an answer for the top, an answer for the bottom, and make a fraction out of it. That'll get around the problem of getting a decimal answer that's not exact. So I'll show you what I mean. Also, another hint, if you actually click into the solution box in the software, it will tell you that the answer's got to be either an integer or a fraction. In other words, they're giving you one more warning that they don't want a decimal approximation. But in general, unless they tell you to round it, they do not want a decimal approximation. So I would calculate the answer for the top, the answer for the bottom, and just turn it into a fraction. That's what you need to do in a problem like this. So if you're just doing the numerator, remember Shift 2 is for a combination. So you put in the 6, hit Shift 2 for combination. The smaller number is 4, so you type that in, hit equal to. Then the dot is a multiplication, so you press the multiplication button, and then you do the second combination. So you do 5, Shift 2, 3, and then you press equal, and that will give you an answer of 150 for the numerator. So just take that 150 and write it down. Then you go to the denominator, and it's a combination, so you do Shift 2, so it's 11, Shift 2, 7, and you press equal, and you get 330. So the answer is 150 over 330. Now that actually reduces to 5/11ths, but WebAssign doesn't really care if you reduce or not. So if you wrote 150 over 330, it would also accept that. What it will not accept is a decimal approximation. If you get the equivalent of 5 divided by 11 written as a decimal, it's rounded off in your calculator display, and that is not an exact answer. So just remember, in these types of problems, do the top and the bottom separately and just make it into a fraction and enter that fraction as your answer. 25. How many combinations are possible? Assume the items are distinct. 7 items chosen 3 at a time. Okay, this is a combination, so you'll know you're going to write it as a combination. It's a combination of 7 things taken 3 at a time. Your calculator presses are 7, Shift 2 is combination, 3, equal to, and the answer is 35. 26. A student downloaded 5 music files to a portable music player. In how many different orders can the songs be played? This is a problem where order is important, and you're arranging all 5 files, so it's just a factorial. It's just 5 factorial. If you're arranging a group of things and order matters and you're arranging all of them, it's a factorial. Well, factorial is Shift 3 on your calculator, so you put in 5, Shift 3, and it'll give you 120. Number 27. A gold, a silver, and a bronze medal are awarded in an Olympic event. And how many possible ways can the medals be awarded for a 200-meter sprint in which there are 14 runners? First thing if you've got a gold, silver, and bronze medal, that means there are 3 types of medals. Order does matter here because getting a gold medal for finishing first is different than getting a silver medal for finishing second, which is different than getting a bronze medal for finishing third. Since order matters, this will be a permutation problem. So we just have to figure out what numbers to use for our permutation. Because there are 14 runners, that will be the first number in the permutation calculation. And because there are 3 medals, that will be the second number in the permutation calculation. And as you should be familiar with now, when you're doing a permutation on your calculator, you use Shift 1. So you type in 14, do your Shift 1 combination for permutation, then enter the 3, which is a small number, and press equal to, and it will give you 2,184. I will say there's an alternate way to do this. You could go straight to the counting principle. If you do that, you think of this as being a 3-stage experiment. You're going to choose your gold medal winner, then you're going to choose your silver medal winner, and then the bronze medal winner. So the number of ways to choose the gold medal winner, if there are 14 runners, any of those 14 could be in that first place position. But once somebody finishes in the first place position, they can't also finish in the second place position, so there are only 13 choices for the silver medal. And once someone has been chosen to finish first place and second place, there are only 12 left to finish third place. And if you take 14 times 13 times 12, which is what the counting principle says, you also get 2,184. So whichever way you prefer. 28. A professor gives his students 9 essay questions to prepare for an exam. Only 2 of the questions will actually appear on the exam. How many different exams are possible? Keep in mind you're choosing 2 questions out of 9, but it really doesn't matter which question you choose first. So if somebody makes out a test for you, it's not really important which one's first. It's just which set of questions you get. So the professor has a set of 9 essay questions. He's actually only going to pull 2 of them and put on the test. So that's a classic combination. You're choosing 2 things out of 9. So it's a combination of 9 things taken 2 at a time. Remember, Shift 2 is the code for the combination on your calculator. So you do 9 Shift 2, 2 equals, and you'll get 36. So there are 36 possible different exams that the professor can give you if the professor is drawing 2 questions from a pool of 9 questions. 29. A dodecahedral die, that's one with 12 sides, numbered 1 through 12, is tossed once. Find the probability that the number on the upward face is divisible by 4, and enter the probability as a fraction, not a decimal. So if you're rolling a die with 12 sides and numbers 1 through 12, then obviously your die rolls are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the only things possible. You want to know the probability that they're divisible by 4, so you got to figure out which ones are divisible by 4. Well, 4 divides by 4, 8 divides by 4, and 12 divides by 4. So there are 3 numbers in that list that divide by 4. So by the basic probability principle, the probability that the number is divisible by 4 is how many are divisible by 4 divided by how many there could be. So that's 3 twelfths. If you reduce that, you get 1/4, but WebAssign doesn't really care if you reduce, so even if you put in 3 twelfths, you should be okay. 30. 2 regular 6-sided dice are tossed. Compute the probability that the sum of the pips on the upward faces of the 2 dice is the following. And they want to know what the probability is that the sum is 6 in this particular problem. So we're looking for a sum of 6. And you just, if they give you the visualization, you just scan through it and find all the 6 sums. So 1 and 5 is 6, 2 and 4 is 6, 3 and 3 is 6, 4 and 2 is 6, 5 and 1 is 6. That's 1, 2, 3, 4, 5. So the probability of the sum is 6 is the number of 6 sums divided by the number of possible sums. Well, we just counted there are 5 sums of 6, and there are 36 possible rolls when you roll 2 dice. So it would be 5/36. Number 31. A card is selected at random from a standard deck of playing cards. Compute the probability that the card is a 10 and enter the probability as a fraction. Again, you need to know what a standard deck of cards looks like. And remember, the probability that a card is 10 is simply a count of the number of 10s that are in the deck divided by the total number of cards in the deck. Well, of course, there are 4 10s in the deck. So the number of 10s is 4. That's the numerator. And there are 52 cards in the deck. So that's the denominator. So you get 4 52nds. You don't have to reduce your fractions. WebAssign will accept 4 52nds. But if you do reduce it, it would be 1/13. Number 32. Use the data given in the table below to compute the probability that a randomly chosen voter from the survey will satisfy the following and round to the nearest hundred. And that is that the voter is under 39 years old. So the probability that the voter is under 39 years old. So if you look through there, the rows start out 18 to 28. Well, 18 to 28-year-olds are under 39, and 29 to 38-year-olds are under 39. So there are 847 people in the 18 to 28 category. There are 804 people in the 29 to 38 category. So if you add those together, you get 1,651, and there are a total of 3,228 in all. So the probability of voters under 29 is the number of voters that satisfy the condition, which is that they're under 39, over the total number of voters. That's 1651 over 3228. You never round unless it tells you to, and it did here. So if you actually do the division, you get 0.51 to the nearest hundredth. Pay close attention to how they want the answer. By default, it's a fraction, but if they ask you to round, you must round. A survey asked 850 respondents about their highest levels of completed education. The results are given in the table below. If a respondent from the survey is selected at random, compute the probability that the respondent has a high school diploma but not more. Just a high school diploma but not more. And enter the probability as a fraction. So if you read this chart, you can see there are different categories. No high school, associate's degree, all the way up to the PhD or professional degree. The probability that the person has a high school diploma but not more, you've got to look at that category. The person has a high school diploma but not more. There are 234 of those people. And there are 850 respondents, so that would be 234. The number that satisfy what you want, which are the high school diplomas but not more, divided by the total, which is 850. And they wanted it as a fraction. So even though it does reduce to 117 over 425, WebAssign doesn't really require you to do that, so you could certainly write in 234 over 850. But don't give it as a decimal. The probability of an event is given. Find the odds in favor of the event. So it's 0.4. The first thing I would do is think of 0.4 as 4/10 and write it as a fraction. Because the reason I do that is because I know when I defined odds and probability, I use that B over A plus B definition. So if I see 4/10, I'm going to think of the numerator as a 4, and the denominator as being a sum that adds up to 10 that includes the 4. So since there's a 4 up top, I want a 4 down bottom, and it takes a 6 to make the 4 add up to 10. And when we do odds problems, if we're changing a probability to odds, the numerator of the probability is the in favor of number, and the other number in the denominator that's not the in favor of number is the against number. So if I want to change that to the odds in favor, remember I write the in favor of number first if I'm writing the odds in favor. I write the against number first if I'm doing the odds against. Here I'm doing the odds in favor, so it'll be the in favor of number written first and the against number written last. So it will be 4 to 6. If I were writing the odds against the event, it would be 6-4. Now, as I've mentioned, there are formulas that will give you that result a little more directly, but in my opinion, this is really the best way to think of this if you want to get this problem without having to memorize very much. Just understand how probabilities and odds are related to each other. To me, this is the best way to do it. And also I'll say that 4 to 6 will reduce to 2 to 3. Anytime you have a common factor in the odds, you can simplify those too. A snack-sized bag of M&M candies contains 10 red candies, 12 blue, 9 green, 11 brown, 5 orange, and 12 yellow. If a candy is randomly picked from the bag, compute A, the odds of getting a green M&M. Okay, green. There are 9 green, and if you add up all the other numbers, there are 50 that aren't green. When you're asked about green, you don't care about the other colors. You just want to know how many there are. So there are 9 green and 59 green. So the odds of getting is the same as saying the odds in favor of getting would be 9 to 50. So what is the probability of getting a green M&M? Well, there are 59 total M&Ms, and 9 of them are green. So the probability of getting a green would be the number of greens over the number possible, which would be 9 over 59.